Hello, so this is video number 2 of section 7.4, and this is the last lecture video of the semester. I think, depends if the proof of theorem 10 goes on a little too long, then I might move the example to a third video, but looking at everything, I think this is the last video. So yeah, I have thoroughly enjoyed having each and every one of you in class. I'm sure from a lot of us, this was our first experience with online courses. I know this was my first real experience with an online course. I mean, certainly last semester, part of the semester was done online, but so yeah, I just want to thank you all for making it a great summer semester. And I hope everyone has a safe and healthy rest of the summer. So, with that said, I've got 2 theorems I want to state on the board. Theorem 9, I'm not going to go over the proof. We really only need this theorem so we can talk about theorem 10. Theorem 10 is what gives us the singular value decomposition of a matrix. And so we're going to discuss mostly about theorem 10, how to prove it. While proving it, we will sort of go over a method for calculating a singular value decomposition, and then we will wrap the video and the course up by calculating a singular value decomposition. So, theorem 9 says that if we have v1 through vn, which is an orthonormal basis for Rn consisting of eigenvectors of the symmetric matrix A transpose A. Remember we showed last video that for every matrix A, the matrix A transpose A is always symmetric. And we arrange these eigenvectors so that the corresponding eigenvalues, where again lambda 1 corresponds to v1, lambda 2 to v2, and so on, are listed in order, so decreasing order. So lambda 1 is the largest, lambda n is the smallest. And then if A has R non-zero singular values, meaning lambda r is the last eigenvalue of A transpose A, which is non-zero, then it turns out that A times v1 plus, or the vectors A times v1, A times v2, all the way up to A times vr form an orthogonal basis for the column space of A. So, like I said, we're not going to go over a proof of this. We're mostly just going to state it because we need it to prove theorem 10. But the, I guess, main points you should remember is that if we take the R non-zero singular values of A and look at the eigenvectors that those singular values corresponded to as eigenvalues of A transpose A, then this set is an orthogonal basis for the column space of A. So keep that in mind. Now I want to clear up some space for some definitions. So theorem 10 states that if I've got any m by n matrix, and again, does not need to be a square matrix with rank R, so that means the dimension of the column space of this matrix has basis of size R, dimension R, then we can decompose A in the following way. A is equal to U times sigma times V transpose, where sigma is a block m by n matrix. So the way we define this is a matrix D. These are matrices and or vectors of zeros. So basically we define sigma to be an m by n matrix, and D is an r by r diagonal matrix whose diagonal entries are the R non-zero singular values of A. So we'll see in a second what sigma looks like, but basically we take this block matrix, we put D in the upper left-hand corner, and D is a square R by R diagonal matrix. And then basically we just fill in zeros in the bottom right of D to make sigma an m by n matrix, to make sigma match the dimensions of A. And so you can see sigma is sort of like an almost diagonal matrix. Remember, like I said, the singular value decomposition is kind of like almost diagonalizing A. And so if we decompose A in this way, then we can guarantee that U is an m by m orthogonal matrix, and V is an n by n orthogonal matrix. And so remember, this last statement actually means that V transpose and V inverse are the same matrix. So this could alternatively be written as U times sigma times V inverse. But so, the decomposition defined by this theorem A equals U times sigma times V transpose is called the singular value decomposition sometimes we'll just abbreviate it as SVD of A. And then these matrices U and V also have definitions which I'm not sure we'll ever use again, but it's worth stating. The columns of U are the left singular vectors of A. And the columns of V are the right singular vectors of A. And so just a quick note about this theorem, and then we'll move on to the proof. Sigma is unique. U and V are not. So what does that mean? This matrix sigma we calculate in the singular value decomposition of A will always be the same matrix, right? Because the singular values of A will never change. The number of non-zero singular values of A will never change. And so therefore, this matrix sigma will always be the same. However, we can find a variety of different matrices U and V that are orthogonal and match the correct dimensions. This is very, very similar to how the diagonalization of a matrix works. That is that when we diagonalize a matrix, remember that the diagonal matrix D that is similar to A, right, is always unique, up to maybe permuting the eigenvalues on the diagonal around. But we can find a variety of different eigenvectors to fill in for the matrices P and P inverse that are diagonalizing A. So, yeah, in that way, it's similar. The reason that this matrix sigma is unique here is because we're always requiring that we put the singular values of A in order on the diagonal of D, right? So the first diagonal entry will be sigma 1, then sigma 2, and this will always stay the same because we're ordering them from greatest to smallest. So we are going to prove theorem 10 now. And this actually has a relatively short proof. And then we'll calculate a singular value decomposition, which, as you will see, is a fairly involved process. So this is proof of theorem 10. So we're going to order the eigenvalues of A transpose A from greatest to smallest. Where A is the M by N matrix stated in the theorem. And we're going to let V1 through Vn be the corresponding eigenvectors, where again the indices match up with the correct eigenvalue eigenvector pair. So this is where we need to apply theorem 9. if we look at the first, or the non-zero eigenvalues of A transpose A, and remember, since the singular values are the square roots of the eigenvalues, right, like we'll have the same number of non-zero singular values and eigenvalues, and the orders of this will match up exactly like we want. Then this set is an orthogonal basis for the column space of A. So what we're going to do is we're going to construct an orthonormal basis U1 through UR for the column space of A, using this basis A times V1 through A times VR. And so notice, doing so in this way, for each vector in this orthonormal basis, remember, this vector is just equal to A times Vi divided by the length of A times Vi. But remember, the length of A times Vi is just equal to the ith singular value of A. So this orthonormal basis, each ui is just equal to the vector A times Vi divided by sigma I. So keep that in mind. And so what we can actually do is rework this to show that sigma I times ui is equal to A times Vi. Right? And so you can see then, like, it's almost an eigenvector for A, but not quite. So this step is kind of weird, and we'll see, this step in the proof is kind of weird, and we'll see how it's somewhat, well, you'll see what I mean in the proof. What we're going to do next is we're going to extend this basis to a basis for Rm in any way we want. So what this means is that if this set has fewer than m vectors, remember all of these vectors are linearly independent, and so what we do is we just, and remember we have this sort of, we have the tools to do this from when we study bases. We just add linearly independent vectors to this set until we have a basis for Rm. But specifically, we want to add vectors in a way that preserves this basis as orthonormal. And then what we're going to do is we're going to let U be the matrix whose columns are given by these vectors. So something in particular to notice about U, U1 through UR defined like this, UR through UM. We don't care how they are defined. We are just defining them to make this an orthonormal basis, which means that U is an orthogonal matrix. So next thing we're going to do is we're going to let V just be the matrix whose columns are given by the n orthonormal eigenvectors of A transpose A. So I'll point out that out there where we want to make sure that each of these vectors is normalized. So our orthonormal eigenvectors for A transpose A. And again, we've ordered them to correspond. So V1 corresponds to the largest eigenvalue, Vn corresponds to the smallest eigenvalue. Then all we want to show is that A times V is equal to U times sigma. And after showing this, it'll be one more quick step to show that, in fact, we can decompose A in this way. So to do that, first I want to calculate A times V. This is equal to A times the matrix where we lay it out like this. And so remember, the first R singular values of A are non-zero, but after that, all of the singular values of A are 0. That means that the lengths of A times each of the remaining vectors is equal to 0, which just means that A times the remaining vectors give us the 0 vector. But notice A times Vi for each of these non-zero singular values is equal to sigma times, or sigma I times Ui. So we can actually rewrite this matrix in this way. Where its first R entries are sigma 1 U1 times sigma 2 U2 all the way out through sigma R UR, or sorry, its first R columns, sigma 1 U1 times sigma 2 U2 all the way out to sigma R UR. And then after that, all of its entries are just 0 vectors. And so now, this is a little weird, but this is actually going to be why we defined our matrix sigma like so. So now notice U times sigma. Well, we've defined U to be the following matrix. And sigma to be this block matrix. So again, remember, this is the matrix D, and then we filled in the rest of sigma with zeros. So what is going to happen when we do this matrix multiplication? Notice that in the first R rows, right, or for the first R, for the first R rows of U, well, sorry, for the first, I'm trying to think how this is gonna, for the first R columns of this matrix, right, we're always gonna match up the correspondingly indexed column U1 through UR with the value sigma 1 through sigma R. But once we take the dot product of any row of U times of U with any row beyond epsilon, we're just going to get zeros. Similarly, all of the terms coming from these vectors U sub R plus 1 through UM are going to match up with the zeros we've added down here. So in this way, these vectors will never actually matter in this product because these vectors are always just going to get zeroed out here. These vectors are always going to match up with these sigmas. And so sure enough, computing this product, you get that this is equal to the following matrix. Which is equal to A times V. And so to wrap it up, remember, V inverse is equal to V transpose, so we can just move this V to the other side of the equation, and sure enough, we can decompose A in the following way. So again, this is like almost diagonalizing a matrix, but not quite. So I just want to wrap this up with calculating a singular value decomposition of a matrix. So we're going to say find an SVD of the matrix A is equal to 3, negative 3, 0, 0. 3, negative 3, 0, 0, 1, 1. So how do we find a singular value decomposition? First things first, we have to find the eigenvalues and unit eigenvectors of A transpose A. So this matrix is A transpose A. So this matrix should have two eigenvalues with two corresponding unit eigenvectors. Probably at this step, I will just state the eigenvalues since it's not really the focus of this problem. So this matrix has ordered eigenvalues. Lambda 1 is equal to 18, and lambda 2 is equal to 2. Doing so, calculating now the corresponding eigenvectors for these matrices, I got V1 was equal to 1, negative 1. And V2 was equal to 1, 1. But remember, we want to normalize these. And so we're actually going to call V1 and V2 the following eigenvectors. We're going to say V1 is equal to 1 over square root 2, negative 1 over square root 2, and V2 is equal to 1 over square root 2, 1 over square root 2. And so now notice V1 and V2 are orthogonal eigenvectors, each of length 1, and so they form an orthonormal set. So the next step, well, we just let V be the matrix whose columns are defined by these vectors. So the first column of V should be the normalized version of V1. The second column of V should be the normalized version of V2. And we found 1/3 of our singular value decomposition. And the diagonal matrix D should contain the corresponding, remember, singular values of A. So where sigma 1 is equal to square root 18, sigma 2 equals square root of 2, are all of the non-zero singular values of A. And so notice here, in this example, all of these singular values of A are all of the non-singular values of A. But it should be pointed out just as a reminder that the diagonal entries on D should only be the non-zero singular values. All right, so next step. we want to fill in the matrix sigma so that it has the same dimensions as A. Assuming I don't accidentally erase A. So notice what we want to do is just add zeros to the rows below D or the columns to the right of D to make sure that sigma has the same dimensions as A. So in this case, D was a 2 by 2 matrix. A is a 3 by 2 matrix, so I just have to add one row of all zeros to sigma. Now sigma is technically a block matrix containing D in its upper left. We've added zeros everywhere else so that its dimensions match A. So now we found 2/3 of our singular value decomposition. So now the next step, I have to make sure I don't accidentally erase. Okay, so we've got, let's see, what do I need for U? I need A times V1. We've got V1 and V2 here. Okay, so next step, we have to calculate U. So for each singular value, that is non-zero, we want to calculate U sub I, remember, which is the ith column of the matrix U, using the formula 1 over sigma sub I times A times VI. And so remember here, this is V1, this is V2. So doing this, U sub 1 is equal to 1 over the square root of 18 times A, 3, -3, 0, 0, 1, 1, times the vector VI, and actually, believe it or not, expanding this out, you should get the vector 1, 0, 0. And so now we calculate U2, which is equal to 1 over the square root of 2 times A times V2. So that's just 1 over root 2, 1 over root 2. And that's equal to the vector. So -3, 3 gives us 0, 0, 1, 1 dot 1 over root 2 gives us 2 over root 2, times 1 over root 2 gives us 2 over 2, which is 1. So that's U1, U2. What I'm going to do to create space, we've got sigma. I'll write V up here. So we've got U1 and U2, but remember, we want U to be an M by M matrix. So the dimensions of U should equal the number of rows of A. So lastly, we need to add we need to add vectors to the orthonormal set U1 through UN R to get an orthonormal basis. Orthonormal basis for RM. So notice right now the set of vectors we have is 1, 0, 0, 0, 0, 1. So generally in this case, this will require a little bit of guess and checking. Often you'll have worked this down that it becomes fairly apparent, like you can find a vector, right? All you need to do is find a vector that's linearly independent to the vectors you currently have. You should be able to just iterate over the standard basis vectors, right? Because if all of these standard basis vectors are in the span of your set, then your set is automatically a basis. So what I'd probably do, and you can see how it's going to work in this case, find a standard basis vector which is not in the span of the set you currently have and add it to the set. Because remember, that's automatically a unit vector. Then what you might have to do is normalize the set afterwards. But in this case, we can extend this to a basis in the following way. Because notice this vector is orthogonal to both of these vectors and certainly is a unit vector. So notice these two vectors we added using the two non-zero singular values of our original matrix. We just basically added on one more vector to make this an orthonormal basis for R3. And so then our matrix U is equal to 1, 0, 0, 0, 0, 1, 0, 1, 0. And wrapping things up, A, which is equal to U times sigma times V transpose. Hello, so this is video 2.1. So at the end of recording the last video, I made a mistake, which I guess you'll actually never see because I'm going to paste this video onto the end. So this is the correct singular value decomposition of A. So this is U times sigma times V transpose. The mistake I had made at the end of the original video was I accidentally had input V in for this matrix instead of V transpose. And so where the negative is very much matters. And so the reason I caught this was I had worked this problem out before, and actually in my notes, the solution is correct. But at the end, I decided, well, you know, I should probably actually check my work and multiply these three matrices to make sure I get A. And in doing so, I caught my mistake. And so I actually, here's my work checking this matrix multiplication. So this is the matrix U times sigma. And then multiplying this matrix times V transpose, you do in fact get A. But this shows that you should always, always, always check your work. So at the end of every decomposition, inverse, diagonalization, everything you find, especially on the final, really make sure you take the time to check your work. Because, you know, especially with a problem like this, it's just like a couple more matrix multiplications you have to perform, and you can verify that what you calculated was correct. And in this case, you know, it definitely helped me out because I could get the correct solution up there. So this now actually wraps up the lecture. So like I said, thank you all for a great semester. If you haven't already looked at the review sheet for the final exam, I highly recommend looking at that. And then keep your eyes open for the final exam. It will be open the last Thursday and Friday of class. And so just a note again, for that exam, I've put a 24-hour time limit on it. And so my goal was, in spirit, for the exam to still be untimed, and I've written it to be significantly shorter than 24 hours. I think in class, I might give it as a 2-hour-long exam, or maybe 2 to 2.5 hour long exam. But I decided I didn't want, you know, I wanted to sort of still make it an exam that you would complete in one sitting. So that's sort of the idea behind the 24-hour time limit. But, you know, certainly I didn't want anyone to be rushed, and I wanted people to have time to upload their solutions, because I know certainly, you know, sometimes working from home, you know, if I've got like a TV and, you stuff to do can sometimes be distracting. So that, like I said, wraps up the semester. Thank you all, and yeah.